Mechanics is the study of motion. It explains how objects move and why they move the way they do. Think about a game of football. Mechanics helps us understand the trajectory of the ball, the force of a kick, and the impact on a player. It's a fundamental science that unlocks the secrets of our universe. Mechanics is everywhere. It's in the graceful arc of a basketball shot, the intricate workings of a clock, and the movement of planets in our solar system. It's the science behind the everyday and the extraordinary. Understanding mechanics is crucial for students pursuing careers in science, technology, engineering and mathematics, or STEM. It's the foundation for fields like aerospace engineering, mechanical engineering and even robotics. In this essay, we'll embark on an exciting journey through the key concepts of mechanics, uncovering its principles and their real-world applications. Get ready to explore the fascinating world of motion. Mechanics is a vast subject, so we divide it into branches. This helps us focus on specific aspects of motion. The main branches are statics, dynamics, kinematics, and kinetics. Statics deals with objects at rest. It helps us understand why bridges stand firm and buildings don't collapse. Imagine designing a skyscraper. Statics ensures its stability and strength. Dynamics, on the other hand, studies objects in motion. It explains how forces cause objects to accelerate or decelerate. Think about a car speeding up or slowing down. Dynamics helps us comprehend these changes in motion. Kinematics focuses on the geometry of motion. It describes an object's position, velocity, and acceleration without considering the forces involved. Picture a train traveling along a track. Kinematics helps us track its movement over time. Kinetics delves into the forces that cause motion. It explores the relationship between forces, mass, and motion. Consider a rocket launching into space. Kinetics helps us understand the powerful forces propelling it upward. Kinematics is like the language of motion. It helps us describe how objects move using precise terms and concepts. Let's explore three fundamental types of motion: rectilinear motion, projectile motion, and circular motion. Rectilinear motion is the simplest type of motion. It's the movement of an object in a straight line. Imagine a car driving down a straight road. Its motion can be described using concepts like displacement, velocity, and acceleration. Projectile motion is a bit more complex. It involves objects moving in a curved path under the influence of gravity. Think about a baseball hit into the air. Its trajectory or path is a perfect example of projectile motion. Circular motion describes objects moving in a circular path. Imagine a Ferris wheel rotating steadily. The passengers on the wheel are experiencing circular motion. We use terms like angular velocity and centripetal acceleration to describe this type of motion. Sir Isaac Newton, a brilliant physicist, revolutionized our understanding of motion with his 3 laws of motion. These laws form the bedrock of classical mechanics. Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This is often called the law of inertia. Think about a book resting on a table. It won't move unless someone or something applies a force to it. This is inertia at work. Newton's second law of motion explains how force is related to mass and acceleration. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Imagine pushing a shopping cart. The harder you push, the faster it accelerates. Heavier carts require more force to achieve the same acceleration. Newton's third law of motion states that for every action there is an equal and opposite reaction. When you jump on a trampoline, you exert a downward force on it. The trampoline in return exerts an equal and opposite upward force, propelling you into the air. Section 5. Work, energy, and power. Work, energy, and power are interconnected concepts that help us understand how objects move and interact with their surroundings. Let's break down these concepts. Work in physics refers to the force applied over a distance. Imagine lifting a heavy box. You're doing work because you're applying an upward force and moving the box upward. Energy is the capacity to do work. It exists in various forms, including kinetic energy, energy of motion, and potential energy, stored energy. A moving car possesses kinetic energy, while a stretched rubber band stores potential energy. Power is the rate at which work is done or energy is transferred. Think about two cars with the same mass accelerating to the same speed. The car that reaches that speed faster has a higher power output. These concepts have numerous applications in our daily lives. From the engines that power our vehicles to the appliances in our homes, work, energy, and power are essential for understanding how things function. Section 6. Conservation laws in mechanics. Conservation laws are fundamental principles in physics that state that certain physical quantities remain constant over time within a closed system. In mechanics, we encounter two crucial conservation laws: conservation of energy and conservation of momentum. The law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. Imagine a roller coaster. As it climbs the track, its potential energy increases. As it races downhill, potential energy is converted into kinetic energy. The law of conservation of momentum states that the total momentum of a closed system remains constant if no external forces act on it. Momentum is a measure of an object's motion and is calculated as the product of its mass and velocity. Imagine two billiard balls colliding. The total momentum before the collision is equal to the total momentum after the collision. This principle governs the motion of objects after they interact. Section 7. Exploring rotational motion. So far, we've primarily focused on linear motion, motion along a straight or curved path. Rotational motion, on the other hand, involves objects spinning or rotating around an axis. Think about a spinning top or the Earth rotating on its axis. These are examples of rotational motion. To describe this type of motion, we use concepts like angular velocity, how fast an object is rotating, and angular acceleration, the rate of change of angular velocity. Moment of inertia is a crucial concept in rotational motion. It's a measure of an object's resistance to changes in its rotational motion. Objects with a higher moment of inertia are harder to spin or stop from spinning. Torque is another important concept. It's a measure of the force that causes an object to rotate. Imagine using a wrench to tighten a bolt. You're applying torque to the bolt, causing it to rotate. Section 8. The mystery of gravity. Gravity is a fundamental force of nature that attracts any two objects with mass. It's what holds us to the Earth, keeps the Moon in orbit around our planet, and governs the motion of celestial objects throughout the universe. Sir Isaac Newton, in his law of universal gravitation, stated that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Imagine you throw a ball upward. Gravity pulls it back down towards the Earth. The more massive an object, the stronger its gravitational pull. Johannes Kepler, a German astronomer, formulated 3 laws of planetary motion that describe the motion of planets around the Sun. These laws, based on observations, provided further insights into the nature of gravity. Section 9. Oscillations and Vibrations. Oscillations and vibrations are everywhere in our world, from the swaying of a pendulum to the vibration of a guitar string. These repetitive motions are fundamental to many physical phenomena. Simple harmonic motion, or SHM, is a special type of periodic motion where the restoring force is directly proportional to the displacement from equilibrium. Imagine a mass attached to a spring. When you pull the mass and release it, it oscillates back and forth. We use terms like amplitude, the maximum displacement from equilibrium, period, which is the time taken for one complete oscillation, and frequency, the number of oscillations per unit time, to describe SHM. Oscillations play a crucial role in various fields, including timekeeping, music, and even the behavior of atoms and molecules. Section 10. Fluids in motion. Fluids, which include liquids and gases, are all around us. Understanding how fluids behave is essential for various applications, from designing airplanes to predicting weather patterns. Density, a fundamental property of fluids, is defined as mass per unit volume. It tells us how much mass is packed into a given space. Liquids like water are denser than gases like air. Pressure is another important concept. It's the force exerted by a fluid per unit area. Imagine diving deep into the ocean. The pressure you feel increases with depth due to the weight of the water above you. Buoyancy is the upward force exerted by a fluid that opposes the weight of an immersed object. It's why ships float and why we feel lighter in water. Bernoulli's principle, named after Swiss mathematician Daniel Bernoulli, states that as the speed of a fluid increases, its pressure decreases. This principle is essential for understanding how airplanes generate lift and how fluids flow through pipes. Section 11. Inertial and non-inertial frames of reference. In physics, a frame of reference is a coordinate system that we use to describe the motion of objects. There are two main types of frames of reference: inertial and non-inertial. An inertial frame of reference is one in which Newton's laws of motion hold true. Imagine yourself standing still on the ground. This is an inertial frame of reference. A non-inertial frame of reference is one that is accelerating with respect to an inertial frame. Imagine yourself in a car that is accelerating. This is a non-inertial frame of reference. The distinction between these frames of reference is important because it affects how we perceive and describe motion. For example, if you're in an accelerating car, you might feel a force pushing you back into your seat. This is a fictitious force that arises from the non-inertial nature of the car's frame of reference. Section 12. Central force motion. Central force motion is a special type of motion where an object moves under the influence of a force that is always directed towards a fixed point in space. This fixed point is called the center of force. One of the most famous examples of central force motion is the motion of planets around the Sun. The Sun's gravitational pull acts as a central force, keeping the planets in their elliptical orbits. Understanding central force motion is crucial for analyzing various phenomena, including the motion of satellites, the behavior of electrons in atoms, and the dynamics of binary star systems. Section 13. Conclusion. Embracing the wonders of mechanics. As we've journeyed through the fundamental concepts of mechanics, we've uncovered the principles that govern the motion of objects, from the smallest particles to the largest celestial bodies. We've explored the laws of motion, the concepts of work, energy, and power, and the fascinating world of rotational motion, gravity, and fluid mechanics. Mechanics is not just a set of equations and formulas, it's a way of understanding the world around us. It's the science behind the everyday and the extraordinary, from the flight of a bird to the movement of galaxies. As you continue your studies in science, I encourage you to embrace the wonders of mechanics. Explore its principles, ask questions, and seek out real-world applications. The more you learn about mechanics, the more you will appreciate the beauty and complexity of our universe.